Hi everyone, welcome back again. And let's start paper 2 of AS level chemistry, May-June 2025, variance 23. Let's start with the paper. The chemical properties of an element are related to the electronic configuration of its atom. By the way, electronic configuration means number of electrons. So chemical properties always depends on number of electrons. As long as the number of electrons are same, chemical properties of those elements would be same. All right. Give the full electronic configuration of fluorine atom. Fluorine has an atomic number of 9. So configuration, an examiner is looking for the full electronic configuration. That means we cannot write the shortcut technique of electronic configuration in this part. So we need to write the answer in terms of SP notation. So it's going to be 1s2, 2s2, and 2p5. So that's going to be 9 electrons, okay? And also remember, fluorine is found in group 17 of the periodic table, which is why it contains 7 valence electrons. Next part, deduce the number of pairs of electrons in the second energy shell of an oxygen atom. Second shell is basically the L shell, and L shell contain both S and P subshell. An examiner is looking for the number of paired electrons. That indicates in order to get the answer, I have to write the spin configuration. So this is 1s, this is 2s, and this is 2p. All right. 1s contain 2, 2s contain 2, and 2p contain 5. Oh, examiner is looking for the oxygen atom, right? So it has to be 8. That was my mistake. 8. 1s2, 2s2, and then 2p, 4. So technically, this is n equals to 2. And this n second shall contain 2 paired electrons, okay? So right answer is going to be 2 pairs of electrons. So you have to be very, very careful while reading the question, okay? Draw the shape of the highest energy orbital. Shape, draw karo, highest energy orbital that contain electrons in an atom of calcium. Calcium has an atomic number of 20. Let me configure it. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. That's what we have done in the class, right? And examiner is looking for the highest energy orbital. So highest energy orbital is basically 4s, because the energy of 4s is greater than 3p. All right. According to Auger principle, 4s has the highest energy orbital. All right. So S has a spherical shape. So what we can write here, we need to draw the axis and place this spherical shape structure. So 4s orbital has highest energy among all according to Auger principle, and S has a spherical shape. So we need to draw the spherical shape like this, like we did in the class, okay? Next part of the question is write an equation to represent the first ionization energy of sulfur. Sulfur and first ionization energy, which means 1 electron is lost from its valence shell. So this is 1 mole of gaseous neutral sulfur atom. When it absorbs energy, obviously it's going to lose 1 valence electron. And as a result, it will turn to 1 mole of gaseous monopositive ion. Monopositive ions means carries 1 plus charge, and this is going to be your electron. Okay, and this negative sign is basically the charge of electron. Now the next is explain why the first ionization energy of sulfur is less than first ionization energy of phosphorus. Both sulfur and phosphorus are found in the same period of the periodic table, right? So in the same period of the periodic table, shielding effect remains same. Across the period. Okay, one more thing. Sulfur contain one paired electron in its 3p orbital, so it experiences interelectronic repulsion. So the removal of electron from 3p orbital of sulfur becomes easier. Sulfur contain one paired electron in its 3p orbital, which experiences interelectronic repulsion, also called spin-spin repulsion. And we know that across the period, nuclear charge increases. So sulfur has a greater nuclear charge than phosphorus, but because of this interelectronic repulsion, it outweighs the nuclear charge. So this outweighs the effect of increase in nuclear charge. So the summary is across the period, shielding effect remains same, but nuclear charge increases. Because of this interelectronic repulsion, it outweighs this effect, and therefore ionization energy of sulfur is lower than that of phosphorus. Next part is arrange the three species fluorides, neon, and sodium ion in order of increasing radius. So according to my lecture, the size of anion is greater than that of neutral atom. On the basis of that, fluoride has the largest radius. And according to my lecture, the size of cation is always smaller than that of the neutral atom, which means sodium ion has the smallest radius, and obviously neon has to be here. The size of anion is greater than that of neutral atom. The size of cation is smaller than that of neutral atom. So size of cation is smaller because of a strong proton to electron attraction. Okay. Also, sodium ion has an atomic number of 11, neon has an atomic number of 10, and fluorine has an atomic number of 9. So all of them have same number of electrons, which means all of them are isoelectronic. They are isoelectronic. Which means they contain same number of electrons. Okay. Sodium ion has a smaller radius Because it has more protons than electrons. So it exhibits a strong proton to electron attraction. Okay. Now, fluoride ion has a greater ionic radius because it has less number of protons and more number of electrons. Fluoride has larger radius because it has more electrons. So it has a small nuclear charge. Okay. Let me write it down one more point. It's all right. It's 4 marks. So that's the end of first question. Let's move on to the second one. The chemical properties of oxides are related to the chemical bonding present in these compounds. Period 3 oxide produces a solution with a pH greater than 7. If the solution is greater than 7, then it means it must be an alkaline solution. And obviously, strong alkaline solution. When it is added to water, which means the oxide is soluble in water also. Okay. State the formula of the oxide. So period 3, basic oxide which gives an alkaline solution when dissolved in water is going to be sodium oxide. So examiner is looking for the formula. So we cannot write the name. So formula is sodium oxide. Okay. P4O10 is added to an excess of aqueous NaOH. By the way, P4O10 is basically an acidic oxide. Because it is a non-metal oxide. NaOH is an alkali, which means both of them can react together. Examiner is looking for the equation. So that's very easy. We have done that in class. P4O10 is phosphorus 5 oxide. When it is added to NaOH, it will turn to sodium phosphate. And sodium phosphate has a formula of Na3PO4 and with water. How many phosphorus atom here? 4. So I'll put 4 here. How many sodium atoms here? 12. So I'll put 12 here. How many hydrogen atoms here? 12. So in order to balance hydrogen, I will write 6 here. So that's the balanced chemical equation. Okay, we have done this equation in the class. Table 2.1 shows the melting point of some oxides. Okay, some of them exhibit covalent bonding and some of them exhibit ionic bonding. So these are the covalent bonding ones. These are the ionic bonding ones, right? In detail analysis, these oxides exhibits intermolecular forces. It has no intermolecular forces, and these oxides has electrostatic attraction. So just remember that this entire concept for this part of the question, okay? Examiner is looking for an identify the oxide from table 2.1 that contain the element with the highest oxidation number. Highest oxidation number. So we have done this in class. In sulfur dioxide, sulfur has an oxidation state of +4. In sulfur trioxide, it has an oxidation state of +6. In SiO2, it has silicon has an oxidation state of +4. Na2O में sodium has an oxidation state of +1. MgO may has an oxidation state of +2, and in aluminum it has an oxidation state of +3. So technically, in the entire table, sulfur has the highest oxidation state in sulfur trioxide. So I'm going to write SO3 here. I cannot write the name because examiner has given the formula. So I need to write the formula here. I cannot write the name. A student suggests the following hypothesis. Okay, the hypothesis is melting point of an ionically bonded oxide is only determined by the charge of the cation. If that's the case, okay, that's very absurd statement. But let me read the whole question first. Use table 2.1 to deduce if this hypothesis is true or false. Obviously, it is false. Okay, now the next part of the question is, if there is not enough information to make conclusion, explain your answer. If this is the case, then according to this statement, aluminum oxide should have a high melting point as compared to magnesium oxide, even though aluminum ion has a higher charge, right, as compared to magnesium ion. But look at the data, and data gives you another sort of information. The melting point of magnesium oxide is greater than that of aluminum oxide, despite the fact aluminum has a high charge as compared to magnesium ion, which means this point is invalid and incomplete also. Okay. Because melting point of aluminum oxide is lower than magnesium oxide given in the table. Although charge of aluminum is higher than that of magnesium. Okay. All right. That's the answer. And that's a very interesting information. And one more thing, in order to solve this part, examiner is technically highlighted ionically bonded oxide, which means I have to check only these three. I have to ignore all these covalent oxides. All right. So in among these oxides, aluminum has the highest charge. So according to this hypothesis, it should be the high. It should have a highest boiling point. Sorry, melting point, which is not given in the table. Instead, magnesium oxide has highest melting point. That means this statement is false and it's not the right statement or hypothesis. Okay. Let's move on to the next part of the question. State why zinc oxide is described as Bronsted-Lowry base. Bronsted-Lowry base accepts proton, which means zinc oxide also accepts proton when added to H2SO4. Technically, zinc oxide is amphoteric oxide, so it can react both with acid and alkali. Since examiner is looking for Bronsted-Lowry base definition, which shows proton acceptors are called Bronsted-Lowry base. So according to this point, zinc oxide accepts proton, so it can react with sulfuric acid. All right. Next is aluminum oxide is a white amphoteric compound. State the formula. Examiner is looking for the formula of the aluminum containing species produced when aluminum reacts with NaOH. So it's going to be sodium aluminate, and sodium aluminate has a formula is NaAlOH taken 4. So that's the formula of aluminum sodium aluminate. Okay. State the formula of the aluminum containing salt produced when aluminum oxide reacts with H2SO4. Let me balance the equation first. Aluminum oxide is reacting with H2SO4, converting into aluminum sulfate, and aluminum sulfate is Al2SO4 taken 3 plus water. How many sulfate ions? 3 sulfate ions, put 3 here. How many hydrogen? 6, put 3 here. So that's your balanced chemical equation. An examiner is looking for the formula of aluminum containing salt. So that's the aluminum containing salt formula. So this is Al2SO4 taken 3, that's aluminum sulfate. I hope it makes sense to you. Next question is, different hydrocarbons mixture produced from fractional distillation of crude oil have different uses. So state the compound that is heated with long chain hydrocarbons to produce more useful smaller chain hydrocarbons, alkane and alkene. So that's called cracking, and cracking involves aluminum oxide as a catalyst. So state the compound. Aluminium oxide, which acts as a catalyst. Okay. Next is describe how photochemical smog is produced during the combustion of petrol in the internal combustion engine. So first of all, during combustion of petrol, unburnt hydrocarbons are produced. They will react with oxides of nitrogen. To give pan, also called photochemical smog. Okay. PAN is polyacetyl nitrate. C4H8 is basically an alkene which reacts with excess hydrogen to produce an alkane, C4H10. So this is going to be your alkene. And this is going to be your alkane. So butene is converted into butane. Name the catalyst for reaction 1. Obviously, nickel as a catalyst. An examiner is looking for the name, which means I cannot write the symbol, right? Define activation energy, minimum amount of energy required to proceed the reaction via effective collision is called activation energy. Next part of the question is the Boltzmann distribution for the reaction mixture in reaction 1 is shown in figure 3.1. Use the Boltzmann distribution to explain the effect of adding catalyst on the rate of reaction. When we add catalyst, this is the normal uncatalyzed reaction. And with catalyzed, it has to be like this. So during uncatalyzed scenario, a small fraction of molecules have energy equal to or greater than activation energy. But when we use catalyst, this entire fraction increases. And therefore, greater proportion of particles with sufficient amount of energy to react. And therefore, rate of reaction increases. So what we can write here is area under the curve with energy equal to or greater than activation energy using a catalyst is larger. So greater proportion of particles to react, hence rate of reaction increases. Hence, due to collision frequency, due to higher collision frequency, rate of reaction increases. Okay. Oh, there's a third case. Third question. Let's move on to the fourth one. My goodness, this question belongs to rate of reaction. The reaction between sodium thiosulfate and HCl is monitored at constant temperature. So when this reaction takes place, obviously yellow solid or yellow precipitates of sulfur is observed. This experiment is also called cross experiment, which we have done in O levels theory and AS practical and theory also. And obviously this sulfur dioxide has a pungent smell. Okay. Figure 4.1 shows how the concentration of HCl varies with time. So obviously concentration of HCl with time decreases and therefore gradient decreases and therefore rate of reaction decreases. All right. That's the whole scenario in this graph. But let's talk about this one. Use figure 4.1 to find the average rate of change of concentration of HCl in this reaction. Well, if you need to find out the average rate, you need to remember one formula which we have discussed in the class. The first one is change in concentration over time taken. And time has to be in seconds or minutes. But in this scenario, we have seconds, okay? So from 0 to 100, from 0 to 100. So that's your 100. Okay. So initially the concentration is 1.0 and at 100 seconds, the concentration is 0.5 mole per dm cube. So let me find out the change. It's basically 1 minus 0.5 divided by 100. So obviously it's going to be how much? So 0.5 divided by 100, it's going to be 5 into 10 to the power minus 3. Now, concentration has mole per dm cube and time has second. So unit of rate must be mole per dm cube second inverse. So it's basically 5 into 10 to the power minus 3. Unit is mole per dm cube second inverse. I can write the unit here. The unit of concentration is mole per dm cube and time has seconds. So unit is going to be mole per dm cube second inverse. Now from 400 to 500, from 400 to 500, from 400 to 500, concentration remains same, right? That's, hold on, 0.1 divided by 5 is going to be 0.0 plus 0.1. So it's 0.12. Mole per dm cube or molar is the same thing. Since the concentration is same between these two interval of time, so rate is going to be how much? So rate equals to initial concentration at 400 seconds is 0.12. Final concentration at 500 is again 0.12 divided by 100. 400 and 500 becomes 100. So it's basically 0. So rate is going to be 0 here. And the unit again is mole per dm cube second inverse. All right. So there's a change in concentration over time taken. Time taken is basically 400 to 500 difference, which is 100 seconds. Okay. Use figure 4.1 to identify the limiting reagent. Explain your answer. Obviously, some of the HCl is still left in this experiment, which means HCl must be in excess, and therefore sodium thiosulfate has to be the limiting reactant. So sodium thiosulfate is the limiting reactant. Because HCl is still left after the reaction. Explain why the rate of reaction changes with time. As the concentration of HCl decreases with time, it decreases the gradient and so decreases the rate of reaction. As the concentration of HCl decreases, with time, collision frequency decreases. Gradient decreases. So rate of reaction decreases. Okay. Let's move on to the next part. That's the A part. Oh my goodness. Part 4, the reaction between sodium thiosulfate and HCl is repeated in a second experiment. Okay. In this second experiment, 25 cm cube of 0.05 mole per dm cube sodium thiosulfate reacts with 0.0020 moles of HCl. Calculate the number of sulfur atoms produced. Okay. That's challenging again. That's very challenging. What we can do here is hmm, uh, should I go for the shortcut technique or the long cut? That's what we need to, decide first. Okay. First of all, we have Na2S2O3 versus HCl. So according to the equation, it has 1 mole, it has 2 mole. Examiner has given you the number of moles of HCl. So obviously, moles of sodium thiosulfate is going to be half of it, which is 1 times 10 to the power minus 3. Okay. According to the equation, sodium thiosulfate and sulfur has 1:1 ratio. Not HCl, sulfur. So if you have calculated 1 into 10 to the power minus 3 moles, Obviously, moles of sulfur will remain same. That is 1 into 10 to the power minus 3. Okay, I'm running out of space, but I'll try to adjust here. My third step is 1 mole equals to 6.02 times 20 to the power 23 atoms. So अगर मेरे पास 1 into 10 to the power minus 3 moles हैं, so how much atoms we have? So it's 1 exponent minus 3 into 6.02 exponent 23. So it's going to be 6.02 times 10 to the power 20 atoms. And that's my answer, okay? Atoms of sulfur. I hope it makes sense to you. That's the most easiest way. Explain why rate of reaction cannot be monitored accurately by measuring the volume of SO2 produced in this reaction. SO2 की वजह से क्यों नहीं हम प्रोड्यूस कर सकते? That's the question. Okay. Because sulfur dioxide is soluble in water, so it will dissolve in water, okay? So SO2 is soluble in water. So if SO2 is soluble in water, obviously we cannot find the accurate volume of SO2. Because sulfur dioxide is soluble in water. To give sulfurous acid. Hence, we cannot measure the volume of SO2. Next part, B part, figure 4.2 shows a possible arrangement of outer shell electrons in one SO2 molecule. Sulfur is found in group 16 of the periodic table, so it has six valence electrons, 1, 2, 3, 4, 5, 6. And oxygen has 6 valence electrons, that's 2. So that's the correct shape, correct dot and cross diagram of SO2 molecule. Predict the shape and bond angle of SO2. Shape is non-linear, just like water. And bond angle is 117.5. And that's what I've told you in the class, in the bonding chapter, okay? Use table 4.1 to predict the strength of the dipole moment of SO2, if any, compared to that of water. Explain your answer. This is the band shape geometry of water. This is the band shape geometry of sulfur dioxide. Okay. Both of them have band shape geometry, but here is the dipole moment of oxygen hydrogen bond. Oxygen has an electron negativity of 3.5. Hydrogen has an electron negativity of 2.1. So difference between these two is 1.4. So dipole moment value of each OH bond is 1.4. Here we have 1.4. Here we have 1.4. Now sulfur has an electron negativity of 2.6. And hydrogen has an electron negativity of 2.1. So if you get the difference, it's going to be 0.4, which means the dipole moment of this SO bond is 0.4 and the dipole moment of this SO bond is 0.4, which means this dipole moment is greater than this one. So the strength of dipole moment in OH bond of water is stronger than SO bond in sulfur dioxide, okay? Electron negativity difference between OH is 1.4, which is greater than SO bond. Okay. Okay. This means dipole moment of OH bond in water is stronger than dipole moment of SO bond in sulfur dioxide. Hence, water is more polar than SO2. All right. All right. So that's the end of this question. Let's move on to the next one. That is question number 5. Oh my goodness. That was the 4th question. 5th. W is a colorless liquid. Deduce the empirical formula of W. First of all, let's find out the molecular formula of W. 1, 2, 3, and this one is 4 carbon atom. Count hydrogens. 3, 4, 5, and this one is 6 hydrogen atoms. How many oxygen? 1, 2. 2 oxygen atoms. So this is the molecular formula of compound W. If we need to find out the empirical formula, we need to half it. So it's going to be C3. Oh my goodness. C2 H3O. So that's the empirical formula of W, which is the half of the molecular formula. 2 different reagents are each added to separate sample of W as shown in this. Complete the table 5.1. इससे पहले के complete करें. First of all, let me tell you, this compound has 2 different sort of functional groups. This one is carboxylic functional group. And this one is alkene functional group. Okay. Now, solid sodium is added. Obviously, solid sodium can react with carboxylic acid, but not with alkene. And obviously, when it reacts with acid, it will give you a salt and a bubbles of hydrogen gas. Bubbles of gas is given off also sodium disappears. And the structural formula of organic product when reagent is added to W. So obviously the entire compound can be written as it is. let me hold on. Let me get the structure first. I hope I can write the structure here. Oh my goodness, I cannot. So let me write it down. This is double bond. This is double bond oxygen. This is oxygen and this is Na. So that's the structural formula of compound W when it is treated with solid sodium. Obviously, when treated with aqueous bromine, obviously it will react with alkene only. Carboxylic acid cannot react with aqueous bromine, and therefore bromine decolorizes from red brown to colorless. Don't write bromine decolorizes, okay? This statement is not going to acceptable except in the paper. So red brown to colorless, okay? And the product of this reaction is going to be like this. Carboxylic functional group will remain as it is. Now you need to add one bromine here and one bromine here. All right. Instead of writing these structures, आप इस तरह से भी लिख सकते हो. CH2 double bond C and then CH3 and then COH. So if you want to put aqueous bromine here, put one bromine here and one bromine here, and you can remove one pi bond. So that's also acceptable in the paper. Okay. Both are correct. Okay. Next. B part. Figure 5.2 shows two reactions of W to produce organic compound Y and Z. When this compound is treated with lithium aluminum hydride, obviously this carboxylic acid will turn into primary alcohol. So this reaction is going to be reduction. And this is going to be the primary alcohol, CH2OH. This entire thing will turn to CH2OH. So this is going to be CH2OH. While alkene cannot react with lithium aluminum hydride, which is why it will remain as it is, okay? When this compound reacts with something, this product is formed. So this is ester. This is ester. So ester is formed when alcohol reacts with carboxylic acid. And how many carbon atoms involved in the alcohol? Only one carbon atom alcohol is included, which means methanol is treated with this compound W to give this one, okay? Reduce the number of sigma bonds and pi bonds present in Z. My goodness, sigma bond. This is H, this is H, this is H, count sigma bonds. This is H, this is H, this is H, this is CH2. All right, so let's count the sigma bonds here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 sigma bonds. Whenever we have double bond, it must contain one sigma and one pi. Similarly, it contains one sigma and one pi. So I'm looking for the sigma bond. So sigma bond is basically the single bond. So I need to count entire single bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This one is 13 and this one is 14. Okay. And how many pi bonds? Pi bonds. One pi bond, second pi bond. Only two pi bonds. So that's easy. W reacts with aluminum, lithium aluminum hydride to produce Y. Draw the structure of Y. Obviously, it's going to be the primary alcohol. That is the structure. I need to write it down there. Oh God. There's a CH2OH. Double bond will remain as it is. Okay. Identify the role of lithium aluminum hydride. It's a reducing agent. Suggest the reagent and conditions required when W is converted into Z. So when carboxylic acid and alcohol react together, always esters are formed. During this reaction, during this reaction, an alcohol methanol is used and sulfuric acid acts as a catalyst. Okay. So methanol is used as a reagent and concentrated H2SO4 acts as a catalyst. Okay. How did I find out it has methanol is used during this reaction? See, this is an ester, right? This is an ester. So this is the carboxylic part, and this must be the alcohol part. Now this alcohol part contain only one carbon atom, which means we need one carbon atom ka alcohol, and that is going to be the methanol. Okay, that's what you need to remember. Next part of the question is, this is an ester again. Figure shows the structure of Z, the infrared spectrum of Z. Identify the bonds and functional groups. It's 1100 and it's 1100 and something, 1150, 1140. So it's basically CO of ester. Okay. So D is basically CO of ester. How about C? This is C. C is 16, 15, 16, 1680 centimeter inverse. So C is 1680 centimeter inverse. 1680 centimeter inverse shows double bonded alkene. Okay. So C is double bonded alkene. So I need bond, I need functional group. So these are the bonds, these are the functional groups. Okay. B. B is 15, 16. Oh my goodness. Hold on, hold on. 15, 16, 17. That is 1720. 1720 is basically carbonyl. 1720. Carbonyl, C double bond O, 720. Okay. Carbon double bond oxygen. Carbonyl. And obviously it's an ester to carbonyl of ester. Okay. A. A is exactly 3000 centimeter inverse. That's CH. It's not a very broad P. That means it is CH of alkane. Okay. Z is used to produce addition polymer Q. Draw the repeating unit of Q. So Z is basically this structure, right? Let me draw that structure. so that I can fix it for polymerization. So that is Z. And let me write it down. In addition polymerization, this double bonded CH2 will turn to single bonded. So this, hold on. This bond is shifted. This is C. This is CO, and this one, and this is CH3. Okay, this is the first polymer. Second, oof, this is carbon atom. This carbon atom is CH3. It is double bonded oxygen, single bonded oxygen, and this must be the bond continuation. So this must be the bond continuation. Okay. Okay, taken N. I hope it makes sense to you. What I have written is this whole group will remain as it is. Okay. This C is here. This is CH3. This CH3 is here. And this double bonded will turn to single bond here. That is the whole criteria. Okay. Now this group will remain as it is. This is carbon atom. This is carbon atom. This is CH3. This is CH3. And this double bonded will turn to single bond here. Polyethene is an addition polymer made from ethene. Explain why ethene reacts with electrophile but polyalkenes does not. So ethene contains pi bond. Which can easily react with electrophile. While in polyethene, we have only sigma bond because carbon-carbon is single bond. So we have only sigma bond between carbon atoms. Which cannot react with electrophile. In short, I can say that ethene has contained high electron density region, which can easily accessible to electrophile, whereas in polyethene, there is no high electron density region, which is why electrophile cannot easily interact with polyethene, and therefore addition reaction is not possible in polyethene, while ethene can does. Okay. Question number 6. Define addition reaction. when two or more molecules can react together to give one product. Describe how chlorine is used to produce HOCl. Oh, chlorine, when added to water, it undergoes disproportionation reaction to give HCl and HOCl. Okay. And this reaction is called disproportionation reaction. Between chlorine and water. State one use of HOCl to kill bacteria from water. Kill bacteria in water. Also, we can write used in the sterilization of water. Complete figure 6.1 to show the mechanism for the reaction between HOCl and ethene to produce this. Include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. Now, oxygen is more electronegative element, so it has slight negative charge. Chlorine is less electronegative element, so it has slight positive charge, which means this slightly positive charge chlorine will serve as an electrophile, and therefore, the pi bond of ethene first react with this electron deficient chlorine. At the same time, this bond, OH removes in the form of hydroxide ions. So this is CH2, this is positively charged, this is CH2, and this hydrogen is attached with a carbon atom, okay? And this is OH negatively charged, and this negative charge is a lone pair. Now this lone pair reacts with this electrophile intermediate carbocation, and therefore you will get a product, okay? One, two, three, four. Next, state the reagent and conditions for step one. What's going on with the step one? CH2OH, that is primary alcohol, will remain as it is. There is no change in that. But this chlorine is substituted with cyanide, which means in step one, I'm going to use sodium cyanide and ethanol. Condition is going to be reflux or heat. Okay. Now, in the second step, this CH2OH primary alcohol will remain as it is. There is no change in it. But this CN will turn to CWH, which means in step 2, we are going to do acid hydrolysis. So step 2 is basically the type of reaction, acid hydrolysis. It is also called step-up reaction because you are increasing the number of carbon atoms. Complete the equation to show the reaction in step 2. Well, this reacts with water, converted into primary alcohol will remain as it is. CH2 will remain as it is, and this is CWH along with ammonia. During this reaction, ammonia is also given off, right? Now, since medium is acidic, which means this ammonia will accept this proton. Ouch. We need to use HCl instead of H plus ion. Okay. Not an issue. Now this ammonia reacts with HCl converting into ammonium chloride. So the final product would be ammonium chloride in this scenario. Okay. Oh. Count hydrogen atoms. 2 plus 1, 3. 4 plus 1, 5. So I need to balance hydrogen, which is why I will put 2 here. So it's 4 plus 1, 5. It's 1 plus 4, 5. Number of hydrogen atoms balanced: 1 chlorine, 1 chlorine, 1 nitrogen, 1 nitrogen, 1, 2, 3, 3 carbon atom, 2 oxygen, or 1 hydrogen, 1 oxygen atom. Oh, that's cool. Let me count hydrogen atoms first. 4 plus 1, 5. Over here, we have 5 hydrogen atoms. Hydrogen balanced, 1 chlorine balanced. We have 2 plus 1, 3 oxygen. We have 2 plus 1, 3 oxygen. How many carbon atoms we have? 3. How many carbon atoms we have? 3. That's the balanced chemical equation, guys. That's the end of this question also. That's the trickiest part. And that's the end of this paper.